It has very complex systems. So the building blocks of these systems are shown here. We have a post-AGB star, and its main. We have a post-AGB star, which is an evolved low to intermediate mass star in its most luminous phase of its evolution. Then we have a main sequence companion. The main sequence star is surrounded by an accretion disk from which some bipolar jets are launched. The system is surrounded by a circumbinary disk. There's observational evidence that there's continuous interaction between the circumbinary disk and the central binary, and I indicated this here with the purple streams. And I'm interested in the structure and evolution of the circumbinary disk. We know today of about the total number of post-AGB binary systems that we know of today in the galaxy. The SMC and the LMC are about 300. Numerous studies have already characterized the disk properties. For example, from the infrared excesses in the SED, we can probe whether these systems have a disk. There's evidence for large grains. Dust masses are on the order of 10⁻³ solar masses, and they show signs of stability. Namely, they are in capillary rotation. Also, very recently, Kluska et al. Found that about 10% of the galactic population of post-AGB disks are actually transition disk candidates. Instead of, so they actually have in the SED a lack of near-infrared excess, where as opposed to full disk, where the infrared excess already starts at mid-infrared, at near-infrared wavelengths. So today I will focus on one system, and this system is a full disk based on their SED characteristics. So also a bit of repetition, but why do we care about these systems? So first of all, they give us insight in binary evolution models. I already said that these systems are binary interaction products. So they have had very strong binary interaction very recently, and this is poorly constrained. Also, it's important to study the disk in the stellar evolution from a stellar evolution point of view, as there are disk binary interactions, and this will influence the stellar properties. For example, it will prolong the lifetime of a post-AGB star. And also, these systems are, by studying the disk, we can also put constraints on planet formation mechanisms. Since these disks are very similar to protoplanetary disks around young stars, we can study them, we can use them as a laboratory to study the formation of microstructures. So how can we study these disks? Well, we need high angular resolution observations to probe the details. Distances are about 1 kiloparsec, so a factor of 10 difference with protoplanetary disks around young stars. So actually, we probe with the same observational techniques, we probe approximately the same scales. So with near-infrared interferometry, we probe the disk inner rim, and with mid-infrared interferometry, we probe beyond the disk inner rim, deeper into the disk, at least for full disks. For transition disk, we then probe the disk inner rim. With ALMA in the radio, we can probe the global disk structure, and with adaptive optics instruments, we can probe the surface layers of the outer disk. And I will focus on the VLTI instruments, so near-infrared and mid-infrared interferometry. Yesterday and today, we already had several talks talking about the importance for a multi-wavelength high angle resolution, and they're combining these techniques for one system. So we had Josef Varga talking about a pre-transitional disk with observational data for Pioneer, Gravity, and Matisse. And we can also do this in a post-AGB realm. So we've taken our rich data set for one post-AGB binary system with all current VLTI instruments. And in the wavelength regime that these instruments are operating, the SED shifts from a star-dominated regime in the near-infrared to a disk-dominated regime in the mid-infrared. And I will show some first results of this imaging campaign. We fitted geometric models to the visibility data of the different bands. You see here the data in blue and the best fitting geometric model in orange. Below, I show the images of these geometric models. You can see that the visibility data is fitted quite well. The shape of the overall shape is fitted quite well. But not all individual data points are fitted equally well. So this means that the geometric models are not complicated enough to at least to characterize the full disk structure. In the images, you can see that indeed the mid-infrared emission is more extended compared to the near-infrared ones. So we are really probing a disk and not a shell of dust. You may also notice that the near-infrared images look different from the mid-infrared ones. And this is because we use the families of models to fit the visibility data of the different bands. We try to fit both a single temperature Gaussian ring and a temperature gradient model to fit each individual band. We found that the near-infrared bands were better fitted with a single temperature Gaussian ring, and the mid-infrared bands were better fitted with a temperature gradient model. And this can actually tell us something important about the inner rim structure. We interpreted that the inner rim must be puffed up and rounded in a similar manner as protoplanetary disks around young stars, where it is now quite well established that that a rounded, puffed up inner rim fits the data better than a sharp wall. So we actually need we need to go toward a physical model to understand all physical processes in a disk. So this is my ongoing work. I'm trying to constrain the disk structure of disk targets using radiative transfer models. I show here the currently best fitting model, the results thereof with the data in gray and the best fitting model, radiative transfer model in yellow. So this is still a preliminary result because this is work in progress. So I'm now constraining the disk structure, the disk geometry, and what kinds of dust is actually in there using and try to fit both the SED and the interferometric visibilities at the same time. Future work will involve multi-epoch modeling of this target to model the asymmetric features. This was already shown by Jacques Pluska in a previous talk. We can model then the closure phases together with the visibilities to constrain the different illuminations with Pioneer data. We can also combine this VLTI data with SPHERE and ALMA data to constrain the global disk structure. We can use Matisse observations of transition disk candidates among post-HGB binaries to characterize these transition disks as well. So to estimate the size of the emission and to conclude on the nature of the transition disks. And this will bring me to my summary. So post-HGB binary systems are very complex systems. And there are still many open questions remaining, both in terms of stellar evolution and also in the terms of planet formation. So high angle resolution imaging on the VLTI is actually needed. High angle resolution observations will actually provide us with constraints on how the structure and evolution of these disks are. So we have one full VLTI imaging study on this, on one target, and we concluded that it has a puffed up rounded inner rim. So by continuing studying these systems, we will hopefully eventually be able to conclude on the formation of macrostructures in these disks and conclude on whether these disks are actually second generation protoplanetary disks. And with that, I would like to thank you for your attention, and I will be open to answer your questions.
Okay, thank you for a good talk. Do we have any questions initially in the audience or online? So I'll start with a quick question. So have you taken a look at do the closure phases show any asymmetries?
Yes, the closure phases show asymmetries. The Matisse N-band data is not good enough, but at least the error bars are huge. But for the Pioneer gravity and the Matisse L-band data, there are significant deviations from asymmetry.
So that'll be the next step in your modeling.
Yes.
Any other questions? Oh, yeah, there's one up there from Narcy. Great work. I am curious about the closure phase data. It's
It's the same thing. It's the same question.
So the answer is yes. It will be included in future work. Yeah. And please announce your name and affiliation.
John Young. I was curious about using a different model to fit the near infrared and mid infrared data. So does the near infrared data, I understand that you used a single temperature ring, but is it also consistent with a temperature gradient, but it's just that you don't really detect any emission from the cooler material, and so it's compatible with either model?
Yeah, we can also, so we fitted also the data with a temperature gradient model, also the near infrared bands. We tried to do both in all 4 bands individually, just from the statistics. So it also gives okay results, actually, but just from the statistics, the chi-squares are higher in the near infrared for a temperature gradient model. So, but it's also consistent. You can also fit them all together, basically with a temperature gradient model. But then the near infrared bands are off.
Okay, thank you.
Okay, and if there's no other questions, let's thank the speaker one more time.